Hey guys, welcome back to my YouTube channel. It's 2022. You want to hit that subscribe button and turn on your post notifications so you know every time I post. Alright, hi guys, welcome back to my YouTube channel. So if you don't know me, my name is Camille Lee Smith. I'm the founder of Young Genius Tutoring Services, and I am back today with another video. So I've been seeing your messages and I'm trust and believe I'm trying to get to all of them. So what I have here for you today is a few points that you might need while doing your Redox Equilibria questions, right? So let's get into it, right? So the first part wants you to label the diagram below, this one, and show what's the part of the standard hydrogen electrode. Sometimes you'll see shape. So the standard hydrogen electrode in this compartment right here, you're going to have hydrogen gas pumping in, okay? Hydrogen gas, and it should be at standard temperature and pressure, right? So 1 atmosphere and 298 Kelvin, which is the same as 25 degrees Celsius. In here, you must have 1 molar or 1 mole per decimeter cube of a strong acid. You'll see for the most part HCl or sulfuric acid. So large M means molar, which is mole per decimeter cube, which indicates the concentration. So if you are doing any questions, not necessarily redox equilibria questions, but you come across this big M, means molar, in other words, mole per decimeter cube, right? So yeah. I also, whenever my students are doing rates of reactions questions, when they're asked especially to calculate unit, I say instead of using the whole thing mole per decimeter cube to do your calculations, simply write molar, because at the end of the day, when you work out, for example, the rate constant, when you're doing rates of reactions, you'll be able to, follow the units and not mix them up, because sometimes you'll have to flip them, because molar is way easier to manipulate than moles per decimeter cube, because some people forget that you're not supposed to multiply the 3 in dm cube, but simply add it, right? When you have mole per decimeter cube squared, this would be mole squared per dm to the -6 and not dm to the -9 or dm to the 9. Okay, so yeah, that's just a little tip. So 1 molar or mole per decimeter cube of a strong acid, and we need a platinum electrode, right? So this thing here represents a platinum electrode. Now you should be able to distinguish between the negative electrode and the positive electrode. And I think the biggest concern for students is figuring this out, because when you're doing electrolysis in grade 11, you are used to the cathode being the negative electrode and the anode being the positive electrode, simply because in electrolysis, what you're actually considering would be, all right, excuse any background noise you're hearing. So when you're doing normal electrolysis in grade 11, what you're actually considering was the electrolyte itself, what was the solution inside your beaker. But now, while doing redox equilibria, what we're considering is the actual electrodes and what the electrodes themselves are made of. So now, when you get to redox equilibria, you just need to remember that the anode is going to be a more negative electrode, and the cathode is going to be your positive electrode, basically. So you're probably saying, so come, how am I gonna figure out that, brother? Like, how? So you need to be familiar with the reactivity series. This little thing here, you need to be very much familiar with the reactivity series. So the ones higher in the reactivity series are more negative, so, or more reactive rather. So those will be your more negative electrodes. And How do we know this? Seeing that they're more reactive, they are more likely to go into solution, or they'll more readily go into solution. So that's what you want to think about. And when they go into solution and make ions, what they're doing is leaving behind electrons on the electrode. So if we consider potassium, a potassium electrode against, for example, a tin electrode, our potassium electrode will be your anode and the tin electrode would be your cathode, simply because potassium is higher in the reactivity series. So that will be your more negative electrode. So potassium will have the ability to go into solution more readily and give K+ ions. And in that case, for every K+ ion going into solution, it leaves behind an electron on the electrode. Tin is less reactive, so it won't do that as well as potassium. So as we said, the more reactive metal will be higher in the reactivity series, and that will be your negative electrode. All right, hold on, let me put my phone on silent so I don't get distracted. All right, nice. So now they want you to complete the diagram here to show a complete cell, right? So to show the complete cell, you would use, if you wish to measure the electrode potential for a zinc electrode. Now you probably, let's add a few things to this. Let's use black. So the standard electrode potential of a standard hydrogen electrode is 0 volts, right? So anything you connect this half cell, this is called a half cell, this half cell to, so any other half cell you connect this to complete a cell, will give you the standard electrode potential of whatever electrode you've connected to it. So whatever your voltmeter reading would be, that would be the half cell, the electrode potential of the electrode that is in the other half cell that you've created. That is really not the hydrogen or the standard hydrogen electrode, because the voltmeter reading or the voltage or the electrode potential of the standard hydrogen electrode is 0. So every reading you get here on your voltmeter is actually the electrode potential of this electrode right here. So this is a zinc electrode. So I'll just label this as zinc electrode. And you'll need a connector. This connector is called your salt bridge, right? Excuse my terrible drawing. Salt bridge. I don't think you have to, but this is all right. You can label it. This would be a voltmeter, and that's what you'd get your electrode potential reading from. All right, I think that's everything. Now, zinc, I want you to understand something now. I want you to take some time and try, based on what I've said about determining your anode versus your cathode, which one of these electrodes would be your anode and which would be the cathode. Pause the video, think about it. But I'm going to tell you the answer right now. It's just a little warning. I want you to think about it before I tell you the answer. So zinc would be your anode, because hydrogen is right here in the electrochemical series, and zinc is right here, right? So seeing that zinc is higher in the reactivity series than hydrogen, zinc is more reactive than hydrogen, hence zinc will be our more negative electrode or anode. And that would make the standard hydrogen electrode or cathode. All right, that will make the standard hydrogen electrode or cathode. And seeing that we've gotten this through, and I hope you got it, now the flow of electrons within the cell will always be from the anode to the cathode. So the more negative electrode will always provide your cell with electrons. So electron flow will be from the zinc electrode to the standard hydrogen electrode. Right. Now, cells can be represented in shorthand form using a series of standard conventions. This is if they'll ask you to write or draw the cell diagram. When they say cell diagram, they don't mean this thing that we did up here. Your cell diagram is just representing each half cell separated by the salt bridge to show what the complete cell is. So if we were supposed to say have a cell using a magnesium electrode, I'm using different electrodes because I want to give you practice while we're doing this, right? Versus or with a copper electrode. Which one would be your anode? Which one would be your cathode? All right, the magnesium will be your anode, copper will be your cathode. So whenever you're writing this, I want you to remember now, reduction occurs at the cathode and oxidation occurs at the anode. Oh, I remember it. I remember picture a red cat and an anorexic ox. So an ox, red cat. So red cat, reduction, cathode, and ox, anode, oxidation. Okay. Now match up the symbols or the symbol to its meaning when used to represent an electrochemical cell. Now the salt bridge is represented by a double line or sometimes a dotted line, while the phase boundaries are represented by a single line. So the phase boundary shows you what is being oxidized and which is being reduced. So if we have magnesium and copper, we'll place what's oxidized on the left and what is reduced on the right. So first, our anode is magnesium. So you'll have Mg, then separate that and put Mg2+. How do you know that it is oxidized? Magnesium's oxidation state in elementary form is 0. This is true for all things or all elements in their elementary state. And then here, magnesium ion has a 2+ charge. So as you can see, the oxidation state increased from 0 to 2. An increase represents oxidation. If it is that it is reduced, then that indicates reduction. So I'm going to show you now what it would look like for copper. So we'll divide this by our salt bridge indicator, which would be our double line. And then we'll represent the other phase change, which would be the reduction of copper 2+ ions, for example. So copper 2+ to Cu solid. Now, it's good to write in your state symbols. So you could have Mg solid to Mg2+ aqueous. And whenever something is in its ionic form, most likely it's aqueous because it's placed in water, so it will break apart into its respective ions. So then you'd have copper 2+ and copper solid. All right, so as you can see, copper 2+ ions had a +2 charge at first, then it increased or it decreased to 0 in its elementary state. So seeing that the number 2 is greater than 0, so the number went from 2 to 0, that was reduced. So that indicates reduction. So I hope that was clear. So this is how you would represent your cell diagrams. All right. I think the next thing up is some calculations. So, or not, we're still dealing with the half equations and the different electrode potentials. So they want you to assume standard conditions for all of these. And you can use the table for standard electrode potentials provided to get the values and work these out. But I am just going to Google these values because I completely forgot to get the data booklet. I would advise you though, remember in your examinations to remember to ask for your data booklets because the electrode potential values are given there. Okay, so let's see. I think I should just get it from the internet. The internet. All right. Let me get it. All right, I just Googled one real quick. They look the same for the most part. They have the same information. So this is a chart you'll be looking for: table 5, standard electrode, and redox potentials. Okay, so now that we have this, I can go back to the actual page with the questions. So the first part wants you to calculate the electrode potential of the cell. Now, there are two ways in which you can do it. You could use the algebraic method or you could use the formula. I'm going to show you how to use the formula because it's easier. So the formula will tell you that the E naught of a cell is equal to the standard electrode potential of the cathode minus the E naught value of the anode. So all you do is just put in the values as is. You don't have to change anything, right? So if we have an aluminum electrode and a zinc electrode, which one is higher in the reactivity series? And you'll have to figure that out to tell which one is the anode, which one is the cathode. Usually the anode is written on the left, but it's always good to check. So here, aluminum is oxidized. It goes from 0 to 3+, which is 0 to 3, which is an increase. Here, so this represents oxidation. So that means this aluminum here is your anode. That is if you're not familiar with the reactivity series, right? If you're familiar with it, you know for sure that aluminum is above zinc in the reactivity series. So that all checks out in your head, right? Now zinc here is 2 plus to 0. So from 2 to 0 shows a decrease. So that's reduction. So this is our cathode. So once we've gotten that, we just need the E naught values for each. So zinc would be what we put first. So just like E naught of the cell is equal to the electrode potential of Zn2 plus to Zn. All right, so we'll look for that in our data booklet. So we're looking for zinc, we're looking for zinc, we're looking for zinc. I think I passed it. Or not. Maybe I need to go down. Oh, it's right here. It's the last one, minus 0.76. So we can just write that down. This is going to be minus 0.76 volts. Now put back your minus sign. Then the anode value, you're going to look for that. The anode is aluminum. So we're looking for aluminum 3+ going to aluminum solid. All of these are written in terms of reduction. That's why the minus sign is here, because eventually you're going to have to flip the sign of the anode. So if it were positive, then you would have it being negative. That's if you're doing the algebraic sum method. So to shy away from this or to evade mistakes, whenever like you're doing these questions, I encourage using the formula because they don't have to worry about flipping anything. You just write the values as is. So let me just show you what I'm talking about. So if you look for aluminum, hey, see it here. So as you can see, it's written in terms of reduction. It's minus 1.66 volts anyway. So you see Al3 plus 3 electrons gives you Al solid. This is written in terms of reduction. However, at your anode, oxidation occurs. So if you are using the algebraic sum method, you wouldn't use that. You just use minus 0.76, and that was what we got for zinc. And then instead of putting minus 1.66, you put plus 1.66. But seeing that we're using a formula, we're just going to put negative 1.66. And the formula will do the flipping for us, right? So negative 1.66. So if you put that in a calculator, this would be, hold on. Let me pull up a calculator real quick and hope that it works. I haven't been using this much. Okay, so negative, okay, put it in brackets, negative 0.76, yeah, minus 1.66. That doesn't seem right. Let me use another calculator and just check for sure if that's what you're supposed to get. So minus 0.76 minus 1.66. Yeah, that wasn't correct. It's 0.9. I think it's the way I put it into this calculator. Let's try again. Minus 0.76 minus, open bracket, minus 1.66, close bracket, equal. Yeah, that's not how you put that in. Let me try another calculator on screen. Calculator, the regular old calculator. All right. Negative 0.76, close the bracket, minus 1.66. That's not 1.66, bro. 1.66. Close the bracket. I encourage putting it in like this. 0.9. Nice. The 0 don't have to come before it. I think they just put the 0 there because I didn't put anything. But it's the same thing anyway. So the answer is 0.9. So the E naught of this cell is 0.9 volts. So now they want you to write the positive electrode half equation. The positive electrode is our cathode. So that would be this would be Zn 2 plus 2 electrons, right? That will give you Zn solid. Remember to put your state symbols, the aqueous. So you can check if everything balances out. When something balances out, you have the same number of species as well as charges on both sides. So the charge of zinc on this side is 0. And the charge here is 2 plus, but 2 electrons cancel it out because electrons are negatively charged, right? So you would have plus 2, minus 2 given here, plus 2 and minus 2 together is 0. Or if you want to say 2 minus 2, that's 0. All right, for the negative electrode, that's our anode and that shows oxidation. So this is where Al is going to be oxidized to Al3 plus and 3 electrons, right? And that's supposed to be in the aqueous state. Now, when it comes down to writing the overall cell reactions, you need both electrons to be the same in both equations. So this means Zn2 plus 2 electrons and Zn solid. I don't even have to write that right now. And we have Al and Al3 plus 3 electrons. Now, the easiest way to get these the same is to multiply 3 by 2 or 3 by this equation here and 2 by this equation here. So then what you'll end up with is 3 Zn2 plus 3 times 2 is 6, so 6 electrons. And that's going to give 3 Zn. And for the bottom one, we're going to have 2 Al, then 2 Al3 plus, got me writing all terribly, plus 2 times 3 is 6 electrons. So as you can see now, we have 6 electrons here and 6 electrons here. that's going to allow us to simply just cancel out the electrons. And we can write these together, where our final thing would be 3Zn 2 plus 2Al. Well, put your state symbols aqueous and solid, right? Then we can put the arrow, because that's everything on this side of the arrow. Sorry. That's everything on the left of the arrow. Yeah, so that's everything on the left of the arrow. So we can simply just write those like that. So this. Well, you won't write this in it because we just took it out, and we won't write this on the other side either. And that will leave 3Zn solid state and 2Al 3 plus. And that's your overall cell reaction. All right. Now you're going to do the same thing with this one. If you want to try it on your own, pause the video, try it on your own, and then see if you got everything right? So the E naught potential of this cell, first of all, Cl minus, that's -1, and then it goes to 0. -1 is actually less than 0, so -1 to 0 is actually an increase. So that's the oxidized thing. While here, Fe 2 plus to Fe, that was reduced because we went from 2 to 0, right? So 2 to 0 represents reduction, okay? So that would mean that our negative electrode would be chlorine, or the chloride ion to that. And then you have iron as the positive, right? So same thing, E naught of the cell will be equal to the E naught of the cathode minus the E naught of the anode. So you can just look for these values again. The cathode would be, let's write that there, cat, and this would be anode. So Fe2 plus, and be very much aware that you have a Fe3 plus as well. So please look at these carefully, right? See? So, and we have Fe3 plus to Fe2 plus, but what we're looking for is Fe2 plus to Fe, which is the first one here, which is negative 0.44 volts. So we're going to put that in. So we have minus 0.44 volts minus the anode value. The anode is the chloride ion to Cl2, or a chlorine molecule. So we can look for that one as well. Here we go. That's positive 1.36. So plus 1.36 volts. Don't have to write it down. And then I guess you can put that in your calculators. Let me put it in this one first and then check on my actual scientific calculator. So 0.44, right? It's equal to that. And the answer now, I want to minus 1.36. That's what that says, right? Negative 1.8. Let me put it in my actual calculators. So minus 0.44 minus 1.36. Negative 1.8 is correct. So that would mean that the E naught of the cell is minus 1.8 volts. And then now the positive electrode half equation, the positive electrode would be your cathode. So this would be Fe2 plus 2 electrons. It's easier if you just look at the charge on the ion, and that would give you Fe solid. So ions in the aqueous state, of course, and at a reduced state, Cl minus, right? In the aqueous state will give you Cl2, and before I balance it, and electrons. Now this is going to give you -1, -1, but we have 2 chlorine atoms here, so we need to put 2 chloride ions on this side. So this now becomes 2 minus. So instead of just 1 minus, we need a 2 minus charge balance. So we have to put 2 electrons as well. Now, if we write these two, we have Fe2 plus and 2 electrons. That's going to give you Fe solid, and 2 Cl minus and Cl2 and 2 electrons. They're already the same, so we can just cancel them out, right? So now our final thing would be Fe2 plus 2 Cl minus ions, right? This and this on this side of the arrow. Now what's on the other side of the arrow? Put the arrow, we have this and this on the other side. So we have Fe solid and Cl2 in the gaseous state. These would be aqueous and aqueous. This looks kind of weird, but yeah. Now, these are some multiple choice questions to help you with your calculations. So what is the E naught for the following balanced reaction? Now, if you look here, just figure out from your reaction what is what's oxidized and what's reduced. So I'll just highlight what is oxidized and circle what is reduced. So this is Zn2 plus Zn solid, and it goes to 2 plus. So it's 0 to 2, so that's oxidized. Pb2 plus, so plus 2 to 0, that is reduced, right? So reduced, and this is oxidized. So that means, remember, the E naught of the cell is equal to the E naught of the cathode minus the E naught value of the anode. And so the E naught of this cell would be equal to, the cathode is where reduction occurs. So the Pb2 plus, the Pb2 plus equation is what we're using first. So that's minus 0.126 minus the anode is the other one, so minus 0.763. So if you put that in your calculator, you should get the answer. So minus 0.126 minus 0.763. My calculator is telling me positive 0.637. So the answer is A, right? I'm going to do the same thing over here. Determine what's reduced, determine what is oxidized. First, look at the oxidation states. So this is 0 and it goes to 3 plus, so that's definitely what's oxidized. So that leaves us with this being reduced. So the E naught of this cell will be equal to the cathode value. The cathode is where reduction occurs. So that's the Fe3 plus, and that's going to be 0.771. It's positive, so no need to put a negative sign there, minus the aluminum being oxidized. So that's oxidation at the anode. So that's minus negative 1.660. Put that in your calculator, and you should get the E naught of the cell, which is 0.771 minus negative 1.66. Well, you don't have to put the 0, but if you do, it's no big difference. I got positive 2.431. So the E naught of the cell here, answer is C. And so I hope you're understanding so far. If you have any questions, just drop it in the comments down below. All right. Now they said, what is the E naught for the following balanced equation? So I think we have a bit more to work with. But that's fine. So here we have to just look at the order in which, what is on the left of the arrow versus what's on the right. So this, as I told you, these are already written in terms of reduction. So you can even work it out with the oxidation numbers, but with so many things that are going to take very long, and quite frankly, I'm not in that. So if you look here, it's written the same way here as it is in the standard reduction potential equation down below. So this should tell you that this is what is reduced, and you can easily look at the Fe, that's 0, and it goes to 3 plus, so that means that is oxidized, right? So that would mean oxidation is this one, and that would mean that's the anode. This is reduction, so that would mean that that represents the cathode. So the E naught of this cell, hope you remember the formula, is equal to the cathode value, which would be this one, 0.960 volts, minus the anode value, which is this here, positive 0.771 volts. Then E naught of the cell is therefore equal to whatever you get when you put that in your calculator. So 0.960 minus 0.771, okay? I got 0.189. My voice sounding raspy as usual. So the answer here is A. All right. Now, given the electrochemical reaction shown, if the standard potential or standard reduction potential of Ag plus to silver solid is positive 8, 0.8 volts, and the standard reduction potential of copper 2 plus to Cu is 0.34 volts, what's the E naught of the following cell? All right, call smart goat. Probably not knowing what I'm saying, but that's how I remember the the reactivity series, call smart goats. So call is copper, smart is silver. It's weird, but that's how I remember it. Goat is gold. So copper is above silver, so copper is our anode, silver will be the cathode. Oh, and it's even right here, they give you the cell diagram for this one. So copper, as I said, that's the anode. This is our cathode, silver. So that would mean E naught of the cell is equal to the silver value, which they gave you as 0.80 volts, minus the anode, which is this one, 0.34 volts. So if you put this in your calculator, you'll get the E naught of the cell. And I got the E naught value to be 8 minus 0.34 it is, right? I'm saying right, like I can't hear if you respond. I got positive 0.46. Don't like it. Red? No, blue. 0.46 volts. So that's the answer for that one. And the next one wants you to, given the electrochemical reaction shown, if the standard reduction potential of nickel is negative 0.26 volts and the standard electrode potential of aluminum is negative 1.66 volts, what's the E naught of the following cell? So I hope you're doing them before me, because then if you're not, then you're defeating the whole purpose of this. So identify the anode and the cathode first. So anode here, cathode here. So the E naught of the cell is equal to the cathode value. The cathode is nickel, so negative 0.26 volts, minus the anode value, which is the aluminum value, minus 1.66 volts, or negative 1.66 volts. So the E naught of the cell is equal to whatever you get when you put this in the calculator. So negative 0.26 minus negative 1.66. I got 1.4. 1.4, which is the same as 1.40 volts. Okay, nice. So how you're feeling so far, how you're feeling about electrode potential questions. Let's see what we have next. Two more. All right, two more and then we're done. I didn't want to make this too long, you know, because I know you guys, I know me personally, I can't stay watching this video for hours and hours on end, right? So I try not to make the videos too long now. So given the electrochemical reaction shown, if the standard reduction potential of zinc is negative 0.76 volts, what is the standard reduction potential of magnesium? Now, I hope you see the difference in the question. They're not asking you to work out the E naught of the cell now, you know. They're asking you the standard electrode potential or the reduction potential for one of the electrodes, that is the magnesium electrode. So again, determine which one is your anode, which one is your cathode. In case they don't give you this, because they're not going to always give it to you, remember magnesium is higher than zinc now in the reactivity series. So magnesium is your anode, zinc is the cathode. So now, if we write out the formula, E naught of the cell is equal to the E naught value for the cathode minus the E naught value for the anode. We can do a bit of substitution and then transpose and find the E naught for the anode value, because the anode is magnesium. All right, so what you know? The E naught of the cell is 1.61 volts. That's equal to the cathode value, which is negative 0.76 volts. And we'll subtract the E naught of the anode value. All right, so now this is negative, the anode here. So you need to get it as positive. So to do that, we want to bring it over to the other side of the equation. That's just the easiest way, because if you don't, what you're going to have to do is divide by -1 when you're done. And we don't want to do that. Don't want to take that extra step. So add the E naught of the anode to both sides. So E naught of the anode, and we add it to both sides because we want to keep the equation homogeneous or equal. So equal to minus 0.76 volts minus the E naught. I'm going to put A because I'm going to run out of space, plus E naught of A. So this negative and positive, that going to cancel out each other. So now the E naught of the anode is plus 1.61 volts. See that we're adding 1.61 volts, we're going to subtract 1.61 volts because we want to get it reading as E naught of the anode is equal to something. So we can't have it plus something on this side. So that's why we're getting rid of the 1.61. So now we have negative 0.76 volts minus, not going to make the same mistake I always make and end up jumping 50 million pages down. Just move it over. Nice and nice, nice, nice. So minus 1.61 volts cancels out. So the E naught of the anode is equal to negative 0.76 volts minus 1.61 volts. What you know? Exactly what I was trying to avoid, the page jumping to another one. Let me just move this over. All right, 61 volts. Put this in the calculator. So the E naught of the anode is therefore equal to negative 0.76 minus 1.61, right? I got minus 2.37 volts. So this one. Nice. All right. Now, the last one for no. So given the electrochemical reactivity Sean? Oh, all right. Electrochemical reaction. It's just a typo. No worries, no biggie. Shown if the standard reduction potential of the copper 2 plus, copper solid is positive 0.34 volts, what is the standard reduction potential of tin? All right. Tin is higher than copper in the electrochemical series. You need to study that. So you know that this would be our anode because tin is higher and copper is our cathode. So now they're asking us to find the anode as, again. So we know that the E naught of the cell is 0.48 volts. It's given right here, right? And that's equal to, I don't know why I'm writing up in the air, equal to, oh, my tablet ain't turned properly, equal to the cathode. The cathode here is copper, so 0.34 volts minus the anode value, or I'm going to write E naught of A. And now we can just make E naught of A the subject. So E naught of A, I'm not going to skip the steps. I want to, but I won't. So in order to get E naught of A as positive, we're going to add E naught of A to both sides. So just put E naught of A. This isn't necessarily, the positive is in front of the E naught, but this is already positive 0.48. So that's why I put a plus here. If it were negative 0.48, I would just put negative. You know what? Let's shift it so that you don't get confused. So it could be 0.48 and plus the E naught of A. So we add the E naught of A on both sides. So now what we have working with is 0.48 plus the E naught of A being equal to 0.34 volts. Now we need E naught of the equation to read as the E naught of A, or the electrode potential of the anode, is equal to whatever. So we need to get rid of this 0.48. And seeing that it's a positive 0.48, in order to get rid of it, we'll subtract 0.48 from both sides. So 0.48, and we can put back plus the E naught of A being equal to 0.34 volts minus 0.48. So this 0.48 cancels this one. And now we're left with the final thing being the E naught of A being equal to 0.34 volts minus 0.48 volts. You're going to get a negative number because 0.48 is larger. So 0.34 minus 0.48 is equal to negative 0.14 volts, which would indicate that the electrode potential of the anode is equal to negative 0.14 volts. So now the answer is A. All right, nice. If you see any mistakes, just comment them down below. I'm doing this whole thing for the first time. Like, I'm seeing these questions for the first time. So yeah, I hope this was really helpful, and I saved the best till last. You know what to do. Subscribe to my YouTube channel. The subscription button is the red one just down below before you get to the description section and the comment section, and leave a comment. Yes. And follow me on Instagram at both my business page at young_genius.official, and be social with me on my personal blog page at CAM_, I messed that up. It's _CAM_EO. My name is Camille, by the way. Hey, all right. So remember to like the video and share it with a friend who might need this information. And thank you guys for watching. Until next time, bye.